Pluto is a far-off and stealthy, more humble planet that was once a piece of our close-by planetary gathering. However, continuous, upsetting declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They propose that this cold world is on an expected impact course with Neptune. But how should this actually work, and what might be the consequences of such a giant event? Are we seeing an enchanting, inestimable mannerism, or is there something else to this approaching, interminable mishap? Go along with us as we look at the possible consequences of a Pluto-Neptune influence. Pluto, a past planet that was limited to a dwarf planet, remains a subject of interest and study in the enormous local community. As shown by late conjectures by leading experts, Pluto's circle is hazardously near Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential risky crash between these two planets, which could represent an enormous risk to Earth. But how is such an event indeed even conceivable? Pluto's excursion around the Sun is not normal for that of some other planet in our nearby planetary group. It requires a stunning 248 years to finish a solitary circle. Since its discovery in 1930, it hasn't even completed one full orbit. Anyway, the interest doesn't stop there. Pluto's circle is marked by its especially curved shape, meandering widely from the almost round circles of the major planets. What makes Pluto's circle considerably more amazing is its tilt, which is determined at 17 degrees to the ecliptic plane. The manner in which Pluto follows its way is significantly more inclined compared to other planets. This tendency and unusualness add layers of intricacy to its orbital path. Quite possibly one of the most fascinating parts of Pluto's circle is its crossing point with Neptune's. For around 20 years in each orbit, Pluto actually draws nearer to the Sun than Neptune, testing what we could anticipate from their positions in the planetary group. This prompts the traditional inquiry: why hasn't Pluto crashed into Neptune? The response lies in the gravitational impacts of different planets. The investigation of Pluto's circle started soon after its discovery. Initially, space experts attempted to figure out its interesting way. Dissimilar to different planets, whose circles lie generally near the ecliptic plane, Pluto's circle stands out with its lofty tilt and curved shape. The secret developed with the acknowledgement that Pluto's circle does cross Neptune's. The strength of Pluto's orbit, amidst these complexities, is proof of the intricacies of heavenly mechanics. The three-body problem in space involves deciding how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like attempting to foresee where they will go based on where they started and how they pull on each other. For Pluto's situation, this issue shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a mind-boggling manner. The terms non-concurrent libration, orbital precession, and the VZK wavering are significant for this riddle. According to astrophysicists, what keeps all planets in their orbits is offbeat libration. As for Pluto and Neptune, this term implies that whenever Pluto crosses Neptune's orbit, it is situated somewhere around 90 degrees away from Neptune. This spatial detachment is pivotal in holding their orbits apart. Orbital precession, on the other hand, refers to the upward movement of a body in its orbit. For Pluto, this implies that when it comes nearest to Neptune or some other giant planet, it is situated far above their orbital plane, giving an extra layer of protection from potential impacts. Another critical aspect in this present circumstance is the VZK wavering, named after three specialists, Zell and Kai, who studied how objects move in space. It involves the way three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This pulling influences how they move. For Pluto's case, the VZK wavering helps us understand space researchers can see how even minuscule changes can make a major difference Pluto's way appearing to be unpredictable. In the late 1980s, this swaying helps keep simulations showed something intriguing about Pluto's orbit. The VZK swaying shows that, despite things in space seeming turbulent and unpredictable, capable patterns and rules keep everything in place. These factors assist in keeping Pluto's orbit stable, ensuring that it doesn't slam into Neptune or stray off course. This three-body issue is significant for understanding how these orbits change due to the way space objects pull on one another. Studying this helps us learn more about Pluto, our nearby planetary group, and even far-off universes and their stars. Mathematical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is actually unpredictable, with minor deviations in starting conditions leading to huge differences over millennia. Anyway, these unique properties of Pluto's orbit have been found to maintain stability over unimaginably prolonged timescales, successfully monitoring the disturbance. Later automatic investigations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Neptune has an exceptional relationship with Pluto, where, for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only one at work. Jupiter's gravity also plays a massive role in stabilizing Pluto's orbit. Saturn additionally contributes. These studies show that Jupiter's immense gravity is strong enough to ensure Pluto stays on a steady path for quite some time, even a long period. So maybe Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move securely through space without running into trouble. These peculiarities are crucial for maintaining order and stability in space. Without these mechanisms, the planetary system, as we know it, would be a much fiercer place. Bodies like Pluto could slam into others or be launched out from their stable orbits, setting off a chain reaction with other heavenly bodies. For Pluto, especially with discussions about it potentially ramming into Neptune in the future, understanding its orbit is crucial. This gives a clearer picture of the dynamic nature of the nearby planetary group. The instance of Pluto shows how even the most apparently shaky orbits can come to a condition of balance through the complex cooperation of gravitational forces and orbital mechanics. It also illustrates the importance of continuous observation and investigation of these peculiarities to better understand our place in the universe. Investigating the depths of space frequently drives us to confront the odd idea of divine bodies, and Pluto's orbit is an ideal illustration of the eccentricism. The idea of orbital confusion, which refers to the sensitive reliance of a celestial body's orbit on its initial conditions, is clearly demonstrated. For Pluto's case, this implies that even slight changes in the dwarf planet's position or speed can fundamentally alter its long-term orbit. Using automatic simulations has been hugely helpful for scientists in understanding how Pluto moves in space. These simulations use complex math to show how Pluto and other space objects, like Neptune, pull on each other. By tweaking little details in the simulations, space researchers can see how even minuscule changes can make a major difference in where Pluto ends up. In the late 1980s, these simulations showed something intriguing about Pluto's orbit. However, it has components like offbeat libration and orbital precession to keep it stable. Its orbit can, in any case, be flighty and unusual. In the event that you start with only a little difference in where Pluto is or how fast it's moving, its orbit could end up looking totally changed after a few years. Yet, even with this turmoil, Pluto's orbit remains stable over significant lengths of time, like billions of years. This really means that Pluto's journey around the Sun has a sort of order to it, despite the fact that it appears tempestuous at first. Foreseeing celestial events, particularly when they involve brutal orbits like Pluto's, is a tremendous challenge. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical models provide useful tools for understanding and predicting the future paths of celestial bodies, they also highlight the limits of our predictive abilities. These models rely heavily on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making precise forecasts an overwhelming task. Besides, the chaotic nature of planetary orbits, like Pluto's, reminds us of the ever-changing and dynamic nature of the universe. While we've made immense progress in understanding space, Pluto's case reminds us how much our knowledge of the universe still remains limited. Grasping the gravitational effects of the giant planets on Pluto's orbit gives significant insights into the broader dynamics of the solar system. It shows how the presence and position of every planet can significantly influence the stability and direction of other bodies within the system. So, why are leading astrophysicists lately raising concerns about a potential collision between Pluto and Neptune? Despite all these complicated forces trying to prevent such an event from occurring, Neil deGrasse Tyson, a prominent astrophysicist and a major advocate for cosmology, offers an interesting perspective on the mysteries of our solar system, especially the intriguing case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, offers insightful analysis on the evolving nature of celestial mechanics and the public's interest in the overlooked realms of space. Tyson's position on Pluto's renaming is based on the ever-expanding knowledge of our local solar system. He sees the renaming not as a diminishment, but as a significant adjustment in line with our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and change. He sees the complexities of orbits like Pluto's as an indication of how much more there is still to discover in space. The interest in these questions keeps the exploration of space so intriguing. However, despite Tyson's confidence, his thoughts on Pluto's possible collision with Neptune lay out a different picture. His concerns about the fate of Pluto's orbit suggest that we might still have some more secrets to uncover. Will Pluto collide with Neptune? Or is this just another moment of confusion in the ever-changing universe of space? Only time and further investigation will tell. For now, we are left with a deeper curiosity about how little we still know about our own solar system. We continue to explore these celestial phenomena, bearing in mind the goal of uncovering more of the secrets that lie beyond. The possibility of a Pluto-Neptune collision raises just another question about the puzzling and captivating universe in which we exist. The potential for an accident between Pluto and Neptune raises interesting issues about the dynamics of the solar system, as it challenges traditional understandings of planetary stability. The possibility that two celestial bodies with such incomprehensibly different attributes could collide is both unsettling and fascinating, especially considering the current relative strength of their orbits. Given that Pluto is situated in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be enormous for how we understand gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains a variety of elements and compounds thought to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere made mostly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a giant gas planet, is composed mainly of hydrogen, helium, and other lighter elements with a deep, dense atmosphere. A collision between such disparate bodies would significantly affect their structure and behavior, possibly creating an event that would be observable across vast distances. What makes this hypothetical impact particularly captivating is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only component at play. The presence of Jupiter, the largest planet in the solar system, is another key factor. Jupiter's immense mass, strong gravitational field, and gravitational pull provide a stabilizing effect on Pluto's orbit, preventing it from wandering too far into Neptune's domain. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it unlikely that a catastrophic event will occur between Pluto and Neptune. Despite the apparent risks, ongoing research has also shown that the relationship between Pluto and Neptune is not as simple as a direct impact course. The gravitational resonance between the two planets, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a kind of cosmic lock that keeps them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, while crossing paths in the vastness of space, have never resulted in a collision. The orbital mechanics of these bodies are aligned in such a way that the potential for conflict is minimized. To further understand the complexities of Pluto and Neptune's relationship, it is essential to consider how the behavior of their orbits adjusts over long periods of time. Although Pluto's orbit crosses Neptune's, the two bodies never actually collide because of their gravitational resonance, which ensures they are safely locked in a stable configuration. This remarkable cosmic dance is the result of the two planets' orbital periods being in a 3:2 resonance. Essentially, for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This synchronization ensures that although their paths may cross in space, Pluto and Neptune are always far enough apart at any given point in their orbits to prevent a collision. This resonance is a beautiful example of how the delicate balance of forces within the solar system works to maintain stability. Without this kind of orbital agreement, Pluto would be at risk of drifting into a more chaotic path, potentially interacting with Neptune in a way that could upset the balance of the outer solar system. The gravitational interactions between planets, particularly those as massive as Neptune, Jupiter, and Saturn, also act as protective forces, keeping Pluto in a relatively safe orbit despite its unusual characteristics. In addition to the gravitational forces at play, the overall structure of the solar system also plays a role in limiting the likelihood of catastrophic events. The outer planets, with their immense gravitational fields, act like sentinels, continually shaping and reshaping the orbits of bodies like Pluto. This constant interaction keeps the solar system from descending into chaos, with planets and smaller objects following predictable, though sometimes eccentric, paths. Despite these stabilizing forces, there remains an element of unpredictability in the long-term evolution of the solar system. As we continue to study the behavior of distant bodies like Pluto, we are reminded of how much we still have to learn about the dynamic, ever-changing nature of our universe. While a collision between Pluto and Neptune remains highly unlikely due to their orbital resonance and the gravitational influences of other planets, it still serves as a reminder of the complex and fascinating forces at play in our solar system. The possibility of such an event challenges our understanding and keeps us eager to explore the mysteries of space.